Hi everyone, welcome to the third part of our lecture, and this time we're going to be discussing some equations of states for solids and liquids. In particular, how do we describe or relate the volume of a solid or the volume of a liquid as a function of temperature and pressure. So unlike our gases or vapors, our solids and liquids are not highly sensitive to changes in temperature and pressure. In fact, we can consider that these two types of phases of matter, are generally incompressible. So, in general, minimal lang yung change or very little yung change in volume pag meron tayong change in pressure. Okay, tapos, slightly less ang ating change in volume with respect to temperature compared to gases. Okay, so let's try to prove, okay, that these assumptions will now hold true. So now for our solids and liquids, to describe their change in volume as a function of either temperature and pressure, you have to derive an equation of state. Now for our gases, we have a simplest equation of state, yung ideal gas natin. Okay, and we have a constant, the ideal gas constant, to describe the changes with respect to pressure and temperature. Now for solids and liquids, we define two new variables which will help us determine the change of the volume with respect to either temperature and pressure. So we define the thermal expansion coefficient or the volume expansivity for a solid and liquid, and this is the quantity beta, which is described by 1 over V times change of the volume with respect to temperature at constant pressure. Okay, so the thermal expansion coefficient obtains the change of the volume of your solid or liquid as a function of temperature only. And of course, you have your isothermal compressibility now, which is kappa, which is equal to negative 1 over V times the change of the volume of the substance with respect to the change in pressure at constant temperature. So beta is the change of the volume with respect to temperature, and kappa is the change of the volume with respect to pressure. And naturally, dapat, syempre, negative C, kappa, kasi the higher the pressure, dapat, liliit ng konti C, volume. Now, here are some tabulated values of the thermal expansion coefficient and the isothermal compressibility of multiple substances. Okay, and as you can see, beta is typically very small, okay, to the negative 3 typically. Okay, mga values are even less than this. Okay, and kappa is much smaller. Okay, so typical values of kappa, pascals, units natin is raised to 10 to the negative 10. So sobrang liit ng values nila. Okay, so when using these constants, okay, these are typically still functions of temperature, pero since sobrang late ng values nila, what we do usually is we only evaluate beta and kappa at the initial conditions. So we assume natin at the initial conditions, the values of beta and kappa should hold constant for the whole process. So we can now write a generic equation of state to describe the change of the volume of a fluid with respect to its change in temperature and its change in pressure. Okay, so recall from your degree of freedom analysis, pag alam natin yung composition of fluid, we just need to write, we need to have two variables in order for us to determine the whole state. So for the change in a variable, we need to determine the change in two variables. So yung two variables na gamitin natin is pressure and temperature. So we now write an exact differential where dV is equal to the change in volume with respect to temperature at constant pressure times dt plus the change of volume with respect to pressure at constant temperature dP. Okay. And recall that we have the values of beta and kappa to be the following. So itong term na to, you can have this as beta. The term na to, kappa. So just divide this whole term by 1 over V. Okay, so we can now obtain this particular differential equation. So dV over V is equal to beta dt minus kappa dP. And assuming that beta and kappa are constants, we can now integrate these such that ln V2 over V1 is equal to beta times delta T minus kappa times delta P. Okay, so to illustrate this, let us calculate or try to calculate the molar volume of copper at 1 bar and 500 degrees Celsius. Okay, given that at 1 bar and 20 degrees Celsius, we have the following properties of copper, beta and kappa. and given sa atin yung volume of copper at 20 degrees Celsius. Okay, so for this, again, basic differential equation natin is dV over V is equal to beta dt minus kappa dP. Okay, so dito na ngayon, since constant si pressure, okay, we can cancel this out such that dV over V is now equal to beta dt. And integrating, you can get V2 is equal to V1 times e raised to beta delta t. Okay, so gagawin natin, we can assume that constant yung properties at the initial conditions. So beta and kappa will hold constant all throughout. Okay, so you can get this expression again, V2 is equal to V1 times e raised to beta delta t. Okay, and from here, you can now obtain V2 is 7.28 cm cubed per mole. Okay, so on change of 20 to 500 degrees Celsius, assuming na hindi pa nag-melt si copper at this point, okay, so meron tayong change of uh, 0.17 cm cubed per mole. So maliit lang, given na ang laki ng change in temperature natin. Okay? So now, ano magiging effect if we change the pressure? So let's now try to estimate the molar volume of copper at 100 bar and 20 degrees Celsius. Okay, so again, from our differential equation, or integrated expression, so same temperature, so we can neglect this. Okay, so ln V2 over V1 is equal to negative kappa delta P, or V2 is equal to V1 times e raised to negative kappa delta P. Okay, so dito lang, you just have to be careful with the conversions. Okay, P2 minus P1 natin is equal to 99 bar. Okay, and 99 bar dapat meron tayong conversion. Okay, so 10 to the 5 pascals per bar. And from here, you can now get V2, which is 7.10936 cm cubed per mole. So that increase by 100 times in the pressure, okay, for this copper, parang wala nang nangyaring change in the volume kasi from 7.11 naging 7.10936. So almost negligible na yung change in the pressure. Okay, so assumption natin dito, hindi pa nasisira si copper. So hindi pa siya masyadong, hindi siya nako-compress talaga with respect to pressure. Okay, so we don't account any, we assume na wala mo ng deformations in our solid object. Kaya with this, typically, na-assume natin na most solids are very, very incompressible. So their volumes are not functions of pressure, but rather only of temperature. And even then, kahit temperature siya, maliit lang din yung effect niya. Okay, so next up, we now have a liquid system. So we have 5 kilograms of liquid carbon tetrachloride, which undergoes a mechanically reversible isobaric change of state at 1 bar inside a closed system, during which the temperature changes from 0 degrees Celsius to 20 degrees Celsius. Given this, let us determine the total change in volume, okay, the work, Q, delta H, and delta U of the whole process. Now for this, we can assume that the properties of liquid CCl4 at 1 bar and 0 degrees Celsius are independent of temperature. So beta, Cp, and density, okay, ito yung properties nila at 1 bar and 0 degrees Celsius. Okay, tapos beta and Cp, assume natin na hindi sila nagbabago, okay, all throughout the process. Si density, possible magbago kasi meron tayong change in temperature. So ito yung kakalculate natin ngayon na change in the volume. So how do we proceed from this? So una, kunin natin si specific volume, and the specific volume is the reciprocal of your density. So V1 is equal to 1 over 1590 meter cube per kilogram. Ayan. And from here, we can now get V2. Okay, so integrated expression natin for the EOS for the liquid. So constant pressure, may mawawala yung term natin for kappa. So you will just have V2 is equal to V1 times e raised to beta delta T. Okay, so delta T is equal to 20 degrees Celsius or 20 Kelvin. Kasi same lang naman delta T pag degrees Celsius and Kelvin. And beta is this value. Okay, so ina-assume natin ang constant. And from here, you can now get V2, which is 6.4421 times 10 to the negative 4 meter cube per kilogram. Okay. And from here, you can now get the total change in the volume, okay, which is equal to 5 kilograms, the total mass, times delta V. Okay, so this is V2 minus V1. So the total change in the volume is now 7.64 times 10 to the negative 5 cubic meters. So medyo maliit lang. Okay, kasi liquid nga lang to. Okay, so now for liquids, recall from our heat capacities, okay, that the CP and the CV of a liquid is the same or identical. So isa lang yung heat capacity natin for liquids. So therefore, delta U and delta H are identical, which is just Cp or C delta T. Okay, so 5 kilograms, the total mass, times the heat capacity, times delta T, and the total change in the volume, or the total change in internal energy and enthalpy, are equal to 84 kilojoules. And last, to get the work, since constant pressure, diba, W is equal to negative integral of P dV. Pero isobaric, so pressure, diba, nilabas, so magiging P delta V na lang. Okay, and the delta VT natin is 7.64 times 10 to the negative 5 cubic meters. So P times delta V. So double work natin is 7.64 times 10 to the negative 3 kilojoules. So meron tayong expansion process. Okay, so dapat negative pala to. Okay, and from here you can now get the work. Okay, natin yung work, and we can now get the total heat transfer by Q is equal to delta U minus W. And as you can see, since maliit lang yung value natin ng work, Q is approximately just equal to delta U, and the work of this process is approximately almost negligible. Okay, kasi maliit lang talaga yung value niya compared to the change in the internal energy. Okay, so with this, we assume that liquids are practically incompressible. So yung expansion contraction work nila may often be neglected. Okay, unless sobrang laki nung a change in the volume, which rarely happens. And that's it for this third part of our video. So medyo short lang. Kaya itong discussion natin for equations of states for solids and for liquids. Okay, so we will now have our final video, okay, which is our generalized correlations for both gases and for liquids.